So today we are going to start chapter 4, that is stoichiometry. So what does a chemical reaction equation indicate? The elements and compounds react together in definite proportions. The study of the relationships between the amounts of the reactants and the products. So it's basically the study of relationship that exists between the reactants and the products. And it is referred to as stoichiometry. Basically, it's a word from Greek language, and stoichion means element and metron means measurement. So it's basically the measurement of element. Such a study is essential when quantitative information about a chemical reaction is required. Moreover, it is important to predict the yields of products in chemical reactions. Now we are going to study about mole. So remember that chemists use the mole as the SI unit to weigh and count atoms, molecules and ions. A mole is the amount of substance that contains 6.023 into 10 to the power 23 representative elements. This experimentally determined number is called Avogadro's number. So what is Avogadro's number? It's a 6.023 multiplied by 10 to the power 23. So just as a dozen represent 12 identical things, a mole represents Avogadro's number of particles. And for example, a mole of sodium is 6.023 into 10 to the power 23 sodium atoms, and water is 6.023 into 10 to the power 23 H2O molecules. The atomic mass, formula mass and molecular weight of a substance in grams are equal to 1 mole of the substance. The relationship allows us to convert the mass of a substance to moles and vice versa. Now we have the 1 mole of oxygen atom, 16 gram, 1 mole of oxygen, O2 molecules, 32 gram. So this is how we represent the moles. Now we have the molar volume. So 1 mole of any gas at standard temperature and pressure occupies a volume 22.414 decimeter cube, and this volume is known as molar volume. With the help of this relationship, we can convert the mass of a gas at standard temperature and pressure into its volume and vice versa. For example, 22.414 decimeter cube of any gas is equal to 1 mole, which is equal to 6.02 into 10 to the power 23 molecules. Now we have this example. Determine the volume of 2.5 moles of chlorine molecules at standard temperature and pressure. So 22.414 decimeter cube of Cl2 at standard temperature and pressure is 1 mole, and 1 mole of Cl2 occupies a volume of 22.414 decimeter cube at STP. So 2.5 moles will contain 2.5 multiplied by 22.414 decimeter cube, which is equal to 56.035 decimeter cube. Now we will see the molar mass and density of gases. Density is defined as the mass per unit volume. As molar masses of all the gases occupy same volume at standard temperature and pressure, therefore density of a gas is dependent on its molar mass. So density of a gas can be calculated from its molar mass and molar volume. So calculate the gram molecular mass of a gas which has density of 1.43 gram per decimeter cube at STP. 1 decimeter cube of gas is 1.43. 22.4 decimeter is 1.43 into 22.4, which is equal to 32.032. As 22.4 decimeter cube of a gas is standard temperature and pressure is molar mass. So therefore gram molecular mass of a gas is 32.032. Now we have the stoichiometry calculations and mole ratio. What does a balanced chemical equation tells us? It tells us about that how we will calculate the moles, how we will calculate the number of grams. So it tells us about the amount of reactants, amount of products. So we get the following information. So 2 moles of H2 combined with 1 mole of oxygen from the above equation and 2 moles of water. So 2 into 6.02 10 raised by 23 molecules of hydrogen react with 6.02 10 raised by 23 molecules of oxygen to produce 2 into 6.02 into 10 raised by 23 molecules of water. 4 gram of hydrogen combined with 32 gram of oxygen to produce 36 gram of water. At standing temperature and pressure, H2 combines with O2 to produce 2 into 22.414 decimeter cube of water. When 100 gram of magnesium is treated with dilute hydrochloric acid, what volume of hydrogen can be calculated? Magnesium plus 2HCl gives us MgCl2 plus H2. Moles of magnesium is equal to 100 over 24, which is equal to 4.17. 1 mole of magnesium produces 1 mole of H2, and 1 mole of magnesium produces 1 into 22.4 decimeter cube, and 4.17 will produce 93.408 decimeter cube. So these are the basic calculations that we perform. So there are different calculations, like we have the mole calculation. So in a balanced chemical equation, the coefficient used are taken as mole that indicate the proportion to the next chemical in equation. For example, we have the equation that is CH4 plus 2O2 gives us CO2 plus water. So this reaction indicates that complete burning of 1 mole of CH4 requires 2 mole of oxygen, and 1 mole of methane can produce 2 mole of water and 1 mole of carbon dioxide. So we have the example, how much MgO formed when 4 moles of magnesium react with excess of O2. Also calculate moles of oxygen required. So this is basically the mole to mole calculation. So let's begin. 2 Mg plus O2 gives us 2 MgO. So 2 moles of magnesium produce MgO 2 moles, and 1 mole will produce 2 by 2, and 4 moles will produce 4 moles of MgO. So 4 moles of Mg will give 4 moles of MgO. Similarly, if we have to calculate the oxygen, so we have to see that 2 moles of magnesium are require 1 mole of oxygen, and 1 mole of magnesium will 1 by 2. So 4 moles of magnesium 1 by 2 into 4, that is 2 moles. So that's how we perform that calculations, mole calculations. Now we are moving forward to mole mass calculations. So potassium chlorate is used in making matches and dyes. On decomposition, it produces KCl and oxygen gas. So if 25 gram KClO3 is decomposed, calculate the quantities of the following: how much moles of oxygen are produced and how much mass in grams of oxygen is produced. Okay, 2 KClO3 gives us 2 KCl plus 3 O2, and given mass of KClO3 is equal to 25 gram. Molar mass of KClO3 is, we have to calculate, that is 122.5 gram per mole. So moles of KClO3 is equal to 25 divided by 122.5, that is 0.204 moles. 2 moles of KClO3 give oxygen is equal to 3 moles. 0.204 moles of KClO3 give oxygen. 3 divided by 2 multiplied by 0.204, that is 0.306 moles of oxygen. Now we just the procedure will be same for mass to mole conversion, but you just have to know the given mass, and then you have to calculate the molar mass of the compound, and from the molar mass we will calculate the moles of the compound, and we will just balance, we will find the relationship like we did in the previous procedure. And after that, when you will find the moles of like we have here we have the moles of oxygen, that is 0.306. So now you can again use that mole to mass formula, that is mass of O2 is equal to mole into molar mass. So we will multiply it and you get the grams of the oxygen. So in the next one we are doing the same. This is the equation, and we have 20 grams of H2SO4 and dissolving in water that ionizes completely. So we have to calculate the number of H2SO4, number of H positive and SO4 minus 2 and mass of the individual ions. Mass of H2SO4 is 20 gram, molar mass is 98.016 and number of molecules mass over molar mass into 6.02. So 20 divided by 98.016 is multiplied by 6.02 into 10 to the power 23, which is equal to 1.228 into 10 to the power 23. H2SO4 dissolves in water as follows. H2SO4 gives us 2H positive plus SO4 2 minus. So 1 mole of H2SO4 is equal to 2H positive ions. And 1.228 into 10 to the power 23 moles of H2SO4 is equal to 2 into 1.228 into 10 to the power 23, which is equal to 2.456 into 10 to the power 23 hydrogen ions. 1 molecule of H2SO4 is equal to 1 SO4 2 minus ions. So 1.228 into 10 to the power 23 molecules of H2SO4 is 1.228 into 10 to the power 23 SO4 2 minus ions. Now we have to calculate the mass of the individual ions. So number of ions divided by 6.02 into 10 to the power 23 multiplied by molar mass. So we got the number of ions, that is 2.456 into 10 to the power 23, and we will divide it with Avogadro's number and multiply with the molar mass of an ion, that is 1.008. So we will get for the hydrogen 0.411 and for the sulfate we got 19.58 grams. So first of all we calculated the mass over molar mass ratio, and then we got the relationship between of that H2SO4 with the hydrogen and with the sulfate. So we separately calculated their individual ions in that way, and after that we calculated the mass of the individual ions. Now we have the solution stoichiometry. In solution, the most common concentration unit is molarity. The molarity of a solution is the numerical value of its concentration in mole per decimeter cube. If you read label on the bottle of concentrated H2SO4, you will notice 98% H2SO4 by mass. What does 18 molar stand for? This means there are 18 moles of H2SO4. Similarly, concentrated HCl is 37% and 12.1 molar HCl. This means there are 12.1 mole of HCl in each decimeter cube of the solution. Molarity is the concentration unit in which amount of the solute is expressed in moles and quantity of a solution in decimeter cube. So molarity is defined as the number of moles of solute divided by or dissolved per decimeter cube. So mole of the solute divided by decimeter cube of the solution. So this is a definition of the molarity, and in the solution stoichiometry we basically talk about the molarity. So we have also here some examples, that is of example of urea that has mass 40 grams, and we have to calculate the molar mass, that is 60 gram per mole, then moles of urea 40 over 60, which is equal to 0.667. And then we have the volume of solution, that is 500 divided by 1000, which is 0.5 decimeter cube. Now we will talk about the molarity, is the mole over mole of solute divided by decimeter cube of the solution. 0.667 divided by 0.5, which is equal to 1.334. Now we have another example, that is AgNO3 plus NaCl gives us AgCl plus NaNO3. Thousand centimeter cube of solution is 0.1 mole. 250 centimeter cube is 0.1 into 250 divided by 1000, that is 0.025 mole. 1 mole of AgNO3 is 1 mole of HCl, 0.025 mole of AgNO3 is 0.025 mole of HCl. Mass of AgCl will be moles into molar mass. So moles are 0.025 as we calculated, and molar mass is 143.5 of the HCl, so grams will be 3.59. Now we will use the formula, that is M1V1 over M2V2 is equal to N1 N2. Okay, we have the next example, that is what volume of 0.5 molar sodium sulfate will react with 275 centimeter cube of 0.25 molar barium chloride solution to complete precipitation of the barium 2 plus in solution. Na2SO4 plus BaCl2 gives us BaSO4 plus 2NaCl. So we have V2, we have M2, we have N2, we have M1 and we have N1, but we have to calculate the V1. So we simply use that dilution formula, that is M1 V1 divided by N1 is equal to M2 V2 divided by N2. So 0.5 multiplied by V1 divided by 1 and 0.25 multiplied by 275 divided by 1. V1 is equal to 0.25 into 275 divided by 0.5, which is equal to 137.5 centimeter cube. Okay. Now we have the topic, that is limiting and non-limiting reactant. So it's a very interesting topic in the chemistry, in the stoichiometry. So when two reactants are mixed for a reaction, usually one of them reacts completely and other reactant doesn't react completely. The reactant that reacts completely is a limiting reactant, and other that left unreacted is a non-limiting or the excess one. So here we will take the daily life example, that when you are going to make when you are going to make a sandwich, so you are using kebabs and you are using bread. So when the kebabs are they are less amount than the bread, so kebab will be the limiting reactant. Okay, so here daily life example is not given, so I'm not going to quote further examples, but it's for just your understanding that limiting is the one that is limiting the amount of product. Okay, 2H2 plus O2 gives us 2H2O. When 1 mole of oxygen and 1 mole of hydrogen are mixed, all the hydrogen will react completely and oxygen will left unreacted, because for 1 mole of hydrogen, half mole of oxygen is required, which is available, but for complete reaction of 1 mole of oxygen, 2 moles of hydrogen which are not available, that's why H2 is a limiting reactant and O2 is a non-limiting or excess reactant. Now we have to calculate the mass of calcium nitride prepared from 54.9 grams of calcium and 43.2 grams of nitrogen. Moles of calcium is 1.37, moles of nitrogen 1.54, and 3 moles of calcium produce 1 mole, and 1 mole of calcium 1/3, and 1.37 will produce 0.457. So 1 mole of N2 produces 1.54, 1 mole of Ca3N2 1.54. Okay, I think they have something wrong here. Let me see. Okay, 1.37 moles of calcium will produce 0.47, and okay, 1.54 moles of nitrogen produce 0.457 moles. Okay, 1.54 they have to write 0.47 instead. 0.47 has the least amount, so it's a limiting reactant. So the reactant has the least amount and it's limiting the reaction, and it's just limiting the amount of product, so it's a calcium nitride. Now we have another important and very interesting topic, that is theoretical yield, actual yield and percentage yield. So we adopted an optimistic approach to amount of the product resulting from the chemical reaction. We assume that 100% of the limiting reactant becomes product. The amount of product as calculated from the balanced chemical equation is the theoretical yield. But the actual amount of product that is practically we are getting from the reaction is actual yield. And always remember that actual yield is always less than the theoretical yield, and it is because in the reaction there are many side reactions, there are many things that are affecting the overall yield. So the yield may be less due to the filtration process or something else. So always the actual yield is always less than the theoretical yield. Quantity of products produced experimentally in a chemical reaction is a actual, and percentage yield is 100 times the ratio of the actual yield to the theoretical yield. Percentage yield is equal to actual yield divided by theoretical yield multiplied by 100. So yield is basically what are we getting as a product in a reaction. Calculate the percentage yield of ozone that can be produced by 10 gram of oxygen. Actual yield is 1.05. So 3O2 gives 2O3. Molar mass of O3 is 48 and mass of O2 is 10 grams. So molar mass of O2 is 32 gram per mole and moles of O2 is 10 over 32. 3 mole of oxygen is 2 mole of O3 and 1 mole of oxygen 2 by 3, and 0.3125 is 10 over 32 into 0.3125, that is 0.208. Mass of O3 produced 0.208 into 48, which is 10 gram. Actual yield is 1.05 grams of O3 and percentage yield is 1.05 into divided by 10 into 100, that is 10.5%. So we just have to find the moles and then we have to find the mass, and after that, when the theoretical mass we have calculated the theoretical mass, then we have to divide the actual yield with the theoretical yield and multiply by 100. Then the answer will come in the percentage, in the ratio, in the percentage. Now we have the last topic of this chapter, that importance of stoichiometry in the production and dosage of medicine. In the production of medicine, the amount of active ingredient is essential to produce desired effects. Stoichiometry ensures the accuracy of drug synthesis. Any deviation can result in the incomplete reaction or contamination with unreacted reactants or byproducts. Stoichiometry allows chemists to precisely control chemical reactions to produce drugs to ensure its efficiency, effectiveness, and safe use. For example, in the preparation of antibiotics, stoichiometry ensures that each dose matches the active ingredient and target bacteria. So, in the use of insulin, the use of insulin relies on the stoichiometry to precise control of blood sugar levels. So basically, stoichiometry helps the chemist to precisely control chemical reaction without any deviation. So it is used in the antibiotics, in the insulin, and in the viral antigens in the preparation of vaccine. So there are three main uses. Now we have the activity, that is synthesis of aspirin. Material required is salicylic acid, acetic anhydride, sulfuric acid, sodium hydrogen carbonate, ice bath, and water filtration setup. We have the formula of salicylic acid, that is C7H6O3, and it will react with the acetic anhydride to give aspirin, that is C9H8O4 plus acetic acid. So what are the steps? Mix reactants in stoichiometry calculated amounts in a flask and add few drops of sulfuric acid to it to catalyze the reaction. So catalyst will be sulfuric acid. Place the flask in ice bath, stir the mixture. The flask will be filled with insoluble aspirin. When the reaction is over and sodium hydrogen carbonate solution to neutralize the acid, filter the aspirin. Calculate the amount of aspirin. Calculate theoretical yield using stoichiometry. Compare the actual yield obtained experimentally with the theoretical yield. So we just have to make that aspirin using salicylic acid and acetic anhydride. And at the end we have to neutralize the reaction with sodium hydrogen carbonate. Then we will filter the aspirin and measure the amount, calculate that amount, and using the formula of the percentage yield we will find that percentage of the aspirin. So this is kind of practical that we can perform in the laboratory. Thank you so much for listening. Have a nice day.